Okay, problem number 2. Determine the resultant force and specify where it acts on the beam measured from point A. So we have a distributed normal loading in here, having an intensity 0 to an intensity 6 kilonewton per meter at point A, and then from point A, 6 intensity kilonewton per meter to intensity 0 at point B. So first, let us try to determine the equivalent resultant force of the distributed loading. So we have the first triangle. So we have F1. F1 is now equal to the area of the distributed loading or of this triangular loading, and that is equal to 1/2 multiply this one by 6 multiply this one by 3, and this is therefore equal to 9 kilonewtons, and this is acting at, so we have 1/3 of 3, which is equal to 1 meter from A. Now, the second distributed loading or uniformly varying loading, so we still have a triangular loading, that is now your F2, and that is equal to the area of the load diagram, and this is 1/2 of 6 multiply this one by 6. So this is equal to 18 kilonewtons. And this is acting at. Okay, so this is 1/3 from point A. 1/3 of 6. And that is equal to 2 meters from point A. Now, so let us try to determine now the resultant force. So the resultant force R is now equal to the summation of forces. So we now have summation of forces in the vertical direction. I'm going to consider that the upward forces or downward forces is positive. So your R is now equal to F1 plus F2. So your R is now equal to F1. So we have 9 plus F2, and that one is equal to 18. Therefore, the magnitude of the resultant is equal to 27 kilonewtons. Now, let us try to determine now the location of the resultant from point A. So we now have your F1. This is now your now, F1 is 1 meter from point A, and F2 is 2 meters from point A. Let us try to determine the resultant force. The location of the resultant force, which is equal to 27 kilonewtons. I'm going to consider now that the resultant is acting at a distance x from point A. of a distance x from point A. So the moment of the resultant about point A is now equal to the summation of moment of all the forces on the system about point A. So we have summation of moment about point A. So I'm going to get clockwise moment to be positive. So the resultant is going clockwise about point A. So we have R, multiply this one by X. And then your F1 is going counterclockwise about point A. And that is minus F1, multiply this one by the moment arm, and that is equal to 1. F2 is going clockwise about point A. So we have F2 and the moment arm is 2 meters. So we have 27x is equal to minus 9 plus, we have F2 is 18, multiply this one by 2. So that the value of x in here is now equal to 1 meter. So the location of the resultant of this distributed loading is 1 meter from point A. Okay, for this distributed normal loading, replace the loading by a single resultant force and specify its location on the beam measured from point O. So if this is now your beam, that is your point O, I'm going to consider this one as point B. That is now your point O, and this one in here is now your point B. So I will going to divide the distributed loading into 4 triangles. So we have one in here is a trapezoidal loading. So that is from an intensity 5 kilonewton per meter to an intensity 2 kilonewton per meter. So I'm going to divide this one into 2 triangles. Okay, so we have this triangle and the other one is this triangle. Also, the loading from intensity 2 kilonewton per meter to 4 kilonewton per meter. So this is now another triangle, and this one is another triangle. Now, let us try to determine now the equivalent resultant force of this distributed loading. So I'm going to consider this one as area 1, and this is now your area 2, this triangle in here. And we now have your area 3, this triangle, so that's your area 3, and this one is now your area 4. So now, this is now your F of 1. So that is the equivalent resultant force of this loading. And let's try to consider that that is F sub 1. So your F sub 1 is equal to the area of the load diagram. And this is equal to 1/2. Multiply this one by 5. Multiply this one by 6. So that is equal to 15 kilonewtons. And this is now acting at. So this is a triangle. This is 1/3 of 6 and that one is 2/3 of 6. Acting at 1/3 of 6, or that is equal to 2 meters from point O. Now for area 2, we now have your area 2. So let us try to consider that the equivalent force of area 2 is F sub 2. So we now have F sub 2. And the equivalent resultant force is again the area of triangle 2. So that is 1/2 of 2. So that is 2. Multiply this one by 6, or that one is equal to 6 kilonewtons. And this is now acting at 2/3 of 6. So that is 2/3 of 6, or this is equal to 4 meters from point O. Next, I'm going to consider now area 3 and the equivalent. This is now the equivalent resultant force is F3. This is now your F3. So the equivalent force F3 is now equal to 1/2 of 2 multiply this one by 3. And this one is equal to 3 kilonewtons. And this is acting 2/3 from point B. 2/3 of 3 from point B. So we now have 2/3 of 3 from point B, or this is equal to 2 meters from B. And we have the last area, and the last area is now, okay, so this is the equivalent force of area 4, and that one is now your F4. So your F4 is now equal to 1/2 of 4 multiply this one by 3. And this one is equal to 6 kilonewtons. And this one is now acting at, so this is now the triangle. So it is acting at 1/3 of 3. It's 1/3 of 3, which is equal to 1 meter from point B. Let us now determine the magnitude of the resultant force. So your R is now equal to summation of forces in the vertical direction, and that considering the downward forces is positive. So your R is now equal to F1 plus, we have F2 plus F3 plus F4. So the resultant force is now equal to 15 plus 6 plus 3 plus 6. This is now the resultant force, which is equal to 30 kilonewtons. 30 kilonewtons. So that is downward. So how are we going to determine the location of the resultant force. Now, your F1. So let us try to consider now that the distance from point O to point B is 9 meters. So your F1 is 2 meters. Okay, so that is 2 meters from point O. So I'm just going to consider this is now your F1. F1, so it is 2 meters from point O. And then your F2 is 4 meters from point O. This is now your F2. And this is 4 meters from point O. And then your F3 is 2 meters from point B. So this is now 2 meters from point B. This is your F3. So this is 2 meters from point B. And then your F4 is 1 meter from point B. We now have your F4. So your F4, that is 1 meter from point B. Hence, we now have the distance of F3 from point O is now equal to 9 minus 2. 9 minus 2 is, that is equal to 7 meters. And the distance of F4 from point O is now equal to 9 minus 1, or that is equal to 8 meters. Since we are getting the location of the resultant referred from point O. Now, so I will now consider that the resultant force is acting at a distance x from point O. This is now the resultant force R. And this is now acting at a distance x from point O. Let's try to get moment of the resultant force about point O. So we have now the moment of the resultant force about point O is equal to the summation of moment of all the forces about the same point O. Considering now clockwise moment as positive. So your R is going clockwise about point O. So R, multiply this one by X. So F1 is clockwise about point O. F1, multiply this one by 2. F2, clockwise, plus F2, multiply this by 4, plus F3, multiply this one by 7, plus F4, multiply this one by 8. So those are the moment R. So your R is 30, X is equal to F1, 15 by 2 plus F2, F2 is 6, 6 by 4 plus F3, that is 3 by 7 plus F4, 6 by 8. Hence, your X is now equal to 4.1 meters from point O. Now, the same problem. Supposing I will going to divide this distributed loading into one uniformly distributed load. One uniformly distributed load and two triangular loading. Now, such that this one in here is now equal to 2 kilonewton per meter. And this one is equal to 5 minus 2. So we have 3 kilonewton per meter. Now your 3 kilonewton per meter. Now I will going to consider this triangular area as the first area, and then this uniformly distributed load as the second area, and another triangular loading which is now the third area. Now let us try to determine now the equivalent resultant force of the first area. So this is the equivalent resultant force of the first area. And this is now your F1. So we have the equivalent resultant force of area 2, and that is now your this is now your F, so I'm going to consider that one as F sub 2. And we now have the equivalent resultant force of the third area. This is now your F3. That is now your F3. Now, such that the first area, F1, your F1 is now equal to 1/2 of 3 multiply this one by 6. And this is therefore equal to 9 kilonewtons. And this is now acting 1/3 of 6, which is equal to 2 meters from point O. Now, the second area, which is a rectangular area, so this is equal to 2 multiply this one by 9. 2 kilonewtons per meter multiply this one by 9 meters, or this is equal to 18 kilonewtons. And this is acting at the centroid, which is 1/2 of 9. And 1/2 of 9 is equal to 4.5 meters from point O. And your F3, again, is a triangular loading. So this is the triangle, 1/2 of 2 kilonewtons per meter, multiply this one by 3. And this is equal to 3 kilonewtons. And this is now acting at 1/3 of 3, that is 1/3 of 3, which is equal to 1 meter from point B. 1/3 of 3 from point B. Now, the resultant now is equal to the summation of forces in the vertical direction. We have downward forces positive. So your R is equal to F1 plus F2 plus F3. So your R is now equal to 9 plus 18 plus 3, or the resultant force is now equal to 30 kilonewtons, and that is going down. So we now have the length of the beam is 9 meters. So your F1 is acting 2 meters from point O. So I'm going to consider this is now your F1. So it is acting 2 meters from point O. We have F, that is F1, and this one is now 2 meters from point O. Your F2 is acting 4.5 meters from point O. So we have your F2, and this one is 4.5 meters. And your F3 is acting 1 meter from point B. So this is your F3, and this is now acting 1 meter from point B. So this is 1 meter. F3 is 1 meter from point B. So this is equal to 1 meter. And therefore, your F3 is now acting 9 minus 1, that is acting 8 meters from point O. So that is 8 meters from point O. Now, let us try to locate the resultant force. So I'm going to consider now that the resultant force R, so this is now the resultant force R, and this is acting at a distance. So this is the resultant force R, and this is now acting at a distance x from point O. So that is now your x. If you try to take the moment of the resultant force about point O is now equal to the summation of moment of all the forces about the same point O. At this time, I'm going to consider clockwise moment positive. So your R multiply this one by X is now equal to F1 multiply this one by 2 meters. And then plus F2 clockwise, multiply this one by 4.5 meters, plus F3 clockwise, F3 multiply this one by 8 meters. So we now have the resultant force is 30. X is equal to F1. 9 multiply this one by 2. Plus F2. 18 multiply this by 4.5. Plus F3. 3 multiply this one by 8. And therefore, the location of the resultant from point O is equal to 4.1 meters. So that is from point O. Okay, next. Replace the loading by an equivalent resultant force and couple moment at point A. So this is your point A. So let us try to replace this one by a resultant force, and that resultant force, the component of the resultant force, I'm just going to consider that this is now your RH. Okay, that is the horizontal component of the resultant. And this is now the vertical component of the resultant force. And let us try to consider this one as our vertical. And then the moment at point A. So that is now the moment of the resultant about point A. So this loading is to be replaced by a resultant force and the couple moment at point A. So first, we have a distributed loading again, which is in trapezoidal shape. So I will going to divide this trapezoidal area into two triangular area. This is now. So we have, I'm going to consider that this one in here is your area 1 and this triangle is your area 2. So that is area 1 and this is your area 2. So this length is 6 feet. So let us try to get the equivalent resultant force of the first area. Now you try to take note that this distributed loading is normal to this member. So it is perpendicular to that member. I'm just going to consider that this is now the equivalent resultant force of the first area. And this is now your F1. And this is now the equivalent resultant force of the second area. and that is now your F sub 2. And this uniformly distributed load, so we have the equivalent resultant force that is equal to F3. So your F1 and F2 is normal to this member. Hence, F1 and F2 are both 90 degrees with this member. Now, let us try to determine now the values of F1 and F2 and F3. So we now have your F1 is now equal to the area of the load diagram. Again, at this time, it is a triangular area. So we have 1/2 of, so this is equal to 100 by 6 feet. So we have 100 pounds per foot, multiply this one by 6. And this one is now equal to, so this is equal to 300 pounds. This is 300 pounds, and this is acting at 1/3 of 6 from point A. So this is acting at 1/3 of 6. So this is 1/3. So it's a triangle of 6, which is equal to 2 meters from point A. We now have your F2, still a triangular area. So this triangle in here is equal to 1/2 of, so that is 50, multiply this one by 6. And this one is equal to 150 pounds. And this is now acting at 2/3 from point A. So that is 2/3 of 6 from point A. That is equal to 4 meters from A. And we now have your F3 is a rectangular loading, and the area is the intensity, multiply this one by the length covered by this distributed loading. So we have 50, multiply this one by 4, and this is equal to 200, and this is equal to 200 pounds at, 2 meters from point B. From point B. Now, so let's try to, we have now your F1. So this is now your F1. Okay, perpendicular. So we now have your F1. And then we now have your F2. So F1 and F2. Okay, both, this is 90 degrees, this one is 90 degrees. That is F1, and this is now your F2. I'm going to change it. So your F1. So F1 is 2 meters from point A. So your F2 is 4 meters from point A. And we now have your F3. So this is now your F3. We now have F3. and this is equal to the location is 2 meters from point B. Now, I will now going to resolve the components of F1 and F2. So I'm now going to resolve the component of F1 and F2 into the vertical and horizontal direction. So this is 60 degrees with the horizontal. So we have 60 degrees. So these are therefore the components of F1 and F2. So we have your F2x, we have your F1x. So this is your F1x. This is now your F2x. We have your F2y. So this is now your F2y. And this is now your F1y. So that is now your F1y. Let's try to determine now the horizontal and vertical components of the resultant force at point to act at point A. So first, your F1x. So your F1x is now equal. So that is 60. Therefore, this one is equal to 60 degrees. Similarly, that is equal to 60 degrees. So your F1x is equal to F1 sine of 60 degrees, or that is equal to 300 sine of 60 degrees. Your F1y is equal to F1. Okay, so the 60 degrees is included with the y in the y direction. So we have cosine of 60 degrees, and that is 300 cosine of 60 degrees. Your F2x is equal to F2 sine of 60 degrees, and F2 is 150 sine of 60 degrees. And your F2y is equal to F2. We have cosine of 60 degrees. 150 cosine of 60 degrees. So, we are now ready to determine the horizontal and vertical components of the resultant force. So we have your R horizontal is now equal to summation of forces in the horizontal direction, considering to the right forces positive. So your RH is now equal to, so we have F1x plus F2x. F3 has no component in the direction of x because it is directed vertically. So your RH is now equal to F1x, 300 sine of 60 degrees plus F2x 150 sine of 60 degrees. And this one is now equal to, so this RH is now equal to 389.711 pounds. And this is going to the right. Your R vertical is equal to summation of forces in the vertical direction. This time, I'm going to consider downward forces as positive. So this is equal to F1y plus F2y plus F3. So that is now your F3. So your R vertical is now equal to F1y is 300 cosine of 60 degrees plus F2y 150 cosine of 60 degrees plus F3, and the value of F3 is equal to 200 pounds. So your R vertical is now equal to 425 pounds. So that is downward. So that the magnitude of the resultant is now equal to the square root of RH squared plus RV squared. And this one is now equal to the square root of 389.711 squared plus 425 squared. So that the resultant force is now equal to 576.628. 576.628. Let's try to determine now the position of the resultant with respect to the horizontal. So that with respect to the horizontal, this is equal to the arc tangent of Ry all over Rx. And that is equal to the arc tangent. So we now have the arc tangent of Ry, or that is now your R vertical and R horizontal. So your R vertical is 425 over R horizontal 389.711. So the angle it makes with the horizontal is equal to 47.48 degrees. Therefore, the resultant R, which is equal to 576.628 pounds, is equal to 57.628 pounds. That is down to the right at 47.48 degrees with the horizontal. That is therefore the resultant force. Now, let's try to determine now the resultant couple moment. So we have the resultant couple moment, which is now your M of the resultant at point A. So we now have the moment of the resultant at point A. So this is now the resultant couple moment. This is equal to the summation of moment of all the forces about the same point. So at this time, I will going to consider again clockwise moment positive. So the moment, resultant couple moment is now equal to summation of moment about point A. Hence, our vertical and our horizontal is acting at point A, so it has no moment. So we have MRA. So we assume that to be a clockwise moment is positive. And then F1, your F1 is perpendicular to this member, and therefore this is now the perpendicular distance from the moment center to the line of action of the force. So F1 multiply this one by 2 meters. Next is F2 plus F2 multiply this one by 4 meters. Okay, so still plus F3 multiply this one by, so that is plus F3. So this is now the moment arm of F3 at about point A. So I'm just going to consider this one in here as X. So this is F3 to be X. So this is 2 meters from point B. This one is 4 feet. So this one in here is 2 meters from this point. So let us try to determine now this distance in here. So what is supposed to be this distance? So what is this distance equal to? So I'm just going to consider this one as X sub 1. So if I will now going to isolate the triangle in here. So this is now the, okay, so this is the member, and that member is 6 feet in length. So we have, this is your point A. Then we now have so this triangle in here. So this is your 6 meters. This one in here is your 60 degrees. Hence, this is now your X sub 1. So if you're going to get cosine of 60 degrees is now equal to X1 all over 6 meters. So your X1 is 6, multiply this one by cosine of 60 degrees, and that one is equal to 3 feet. That is now X1. Therefore, your X is now equal to X of 1 plus X1 plus 2 meters. And that is equal to 3 plus 2, or that is equal to 5 feet. So your X in here is now equal to 5 feet. Hence, the moment, couple moment of the resultant at point A is now equal to F1, and F1 is 300. Multiply this one by 2 plus F2, 150. multiply this one by 4 plus F3, that is 200, multiply this one by X, which is equal to 5. We now have the resultant couple moment acting at point A. And this is equal to 200. That is pounds, that is foot. So it is pound foot, or we can write that as foot pounds. So we have a positive value. Therefore, the assumed direction of the moment, resultant couple moment at point A is a clockwise moment.